reactions here. A lot of people are missing. So we're going to look at redox reactions. So a little bit of lecture first. The redox reactions, we have the combination type redox reactions, combination / decomposition. We had talked about. We had the combustion. There's a single replacement. And then we're going to have two more methods. One is called the chart method. And the other is skeleton redox. Skeleton redox we'll talk about later. We're going to talk about the chart method here for predicting wet products. The chart method is very similar to what we saw for the Bronsted acid base. What was the first step of Bronsted acid base? Yeah, identify, or first we have to inventory it. So in this chart method, we're going to inventory. Second, we're going to use the chart to determine oxidizing agents and reducing agents. Third, we're going to use the chart to pick the strongest oxidizing agent and the strongest reducing agent and react them together. So I'm going to combine the steps. Like I had 7 steps for the acid base, but I'm going to just condense it a little bit here. So we're going to react the strongest OA present and the strongest RA present. The way we react this is not by exchanging an H+, but by combining what we call the half reactions. Half reactions. For look at the half reactions to determine OA and RA in the reverse reaction. So step 4 is to predict the driving force. And so the last step here is determine driving force by stronger OA and stronger RA going to weaker OA and weaker RA. This is driving force. If it's not, if we're going from weak to strong, then there's no reaction. Versus weak, weak to strong, strong, we expect NR. All right, and then the final step is to simplify. You know, simplify means get rid of spectators usually. All right, so this method is very similar to Bronsted. In Bronsted acid, you inventory, and then you use the chart to find the acids and the bases. Then you react the strongest acid with the strongest base present. One of the key differences between Bronsted and this is, for Bronsted, the acid loses a hydrogen, the base gains a hydrogen. For this, what we're going to do is we're going to be combining something called the half reactions. And then we look at the half reactions to determine the OA and the RA in the reverse direction. For Bronsted, we just look at who loses and who gains the hydrogen. And then we determine the driving force. So Bronsted, it's the same. Stronger acid, stronger base, weaker acid, weaker base is the driving force. So we're going to look at some examples here of this. Okay, here we're going to predict the products of this reaction. When we predict the products of this reaction here, it looks as if it's a, what kind of reaction? Looks as if it's a single replacement reaction. If it's single replacement, we get some bizarre products. And so this is one of those ones we saw earlier. You know, single replacement predicts this one to be the RA, this one to be the OA, and this one to be the spectator. That's single replacement. But you should know, what do you think is a better oxidizing agent? Chlorine or potassium ions? Yeah, chlorine's a better oxidizing agent than potassium ions. And so the assigned roles are wrong. Assigned roles are wrong. And so all we do is the chart method for this. Use chart method. In the chart method, we inventory. So we're going to have chlorine, we're going to have potassium ions, we're going to have bromide ions, and we're going to have water. And then we use the chart to determine. And so when I look at the chart, chlorine is an oxidizing agent only. Potassium ions are an oxidizing agent. Bromide is a reducing agent. And water is both an oxidizing agent and a reducing agent. And so chlorine appears on the oxidizer side, as does potassium, as does water. And both bromide and water appear on the reducing side, right side. And then we use the chart to pick the strongest. And so we have three oxidizers, chlorine, potassium ions, and water. And it turns out chlorine's the strongest. Then we pick the strongest reducing agent. It turns out that bromide is the strongest reducing agent. So the most likely reaction here is between these two. And so here you can see it was misassigned here. Because in single replacement, they pick A as the reducing agent and bromide as the spectator. But bromide is not a spectator in this particular case if this reaction has a driving force. So the reaction is this. Chlorine. We look at the chart to get the half reaction. And so this is from the chart. We see that chlorine plus 2 electrons goes to 2 chlorides. And then we see down here bromine plus 2 electrons goes to 2 bromides. Now what we have is we have chlorine and we have bromide present. And so this is what we're going to do. We're going to combine these two, what we call half reactions. And so what I'm going to do is I'm going to reverse this one. Because bromide, I'm going to reverse it because bromide is a reactant, not a product. Not a product. And so what I'm going to do is I'll go chlorine plus 2 electrons yields 2 chlorides. And then I'm going to get 2 bromides goes to bromine plus 2 electrons, like that. The key step when we combine half reactions is that the electrons must balance. Electrons must balance when combining half reactions. If they do not balance, then we multiply by coefficient, which we'll do. Here they're balanced, so we don't have to multiply. What I mean by multiplying is that if they're mismatched, we'll just multiply until they match. Multiply the whole equation by some integer. Now we can combine them. If we combine them, we'll get chlorine, which is going to take the 2 electrons, and then 2 bromides. This is going to produce 2 chlorides plus bromine plus 2 electrons. You see the 2 electrons are going to cancel out, and so the net reaction is chlorine plus 2 bromides yields 2 chlorides plus bromine. Okay, I'm going to look at the half reactions now to figure out, is chloride, is that an oxidizer or reducer going reverse? Because what we're going to do is we're going to look at both reactions, the forward reaction and the reverse reaction, and see which ones favor. And so if I look at chloride here, chloride going backwards, does it lose electrons or gain electrons? It loses electrons, so chloride is what we call the reducing agent. This is Ra. And so the OA and Ra are what we call conjugate pairs. If we look at bromine, if we go backwards for bromine, bromine takes electrons going backwards to form bromide. And so bromide was the Ra, and it makes the conjugate OA, bromine. All right, our original OA is chlorine, and our original Ra is bromide. And so what we can do is we can use the chart to compare this. And when we look at the chart, this is from the chart, chlorine is a more powerful oxidizer than bromine. And so this is a stronger oxidizer, this is a weaker oxidizer. And then when we look at the chart, bromide is a stronger reducer than chloride. Lithium's down here, fluorine's up here. And so we're going from stronger reducer to weaker reducing agent, and therefore we have driving force present. And so the single replacement predicted the reaction wrong because it misassigned the roles. The roles are just whoever is strongest will take that role. And so the actual reaction is going to be between chlorine and bromide. Chlorine is what we're going to say oxidizing bromide to form chloride and bromine. All the exceptions happen because of misassigned roles. So the next exception is this. Do an example of copper solid plus HNO3. Copper, the assigned roles are like this. Assigned roles are copper is the reducing agent, H plus is the oxidizing agent, and nitrate is the spectator. But again, the assigned roles are wrong. This acid is special. this acid is special. It is called an oxidizing acid. All acids are oxidizing. All acids have H+, which is an oxidizer. HCl has H+, HNO3 has H+. HCl, this would be an example of a mineral acid. HNO3 would be an example of an oxidizing acid. In a mineral acid, the H+ is the oxidizer. In an oxidizing acid, the X, the nitrate, is the oxidizer. It turns out that nitrate is a more powerful oxidizer than H+. Nitrate is a more powerful oxidizer than H+. Well, let me put a little asterisk here. That asterisk is nitrate and H+ are required. For this. Well, let me show you in the chart. Let's take a look at the acid-base chart and redox chart here. So H+ is what we call a moderate oxidizer. It's kind of in the middle of the chart here. And so we see 2H+ takes 2 electrons to form hydrogen gas. So H+ is a moderate oxidizer, but there are stronger oxidizers. All these oxidizers above this are stronger than H+. And so as we go up, we can see, do you see way up there what we have? We have nitrate. And so nitrate is a much more powerful oxidizer than H+. How about chloride? Is chloride an oxidizer? No, chloride's not even an oxidizer. Chloride is what we call a reducer. Chloride occurs on the opposite side of the chart here. And so this is another example of a misassigned role. When I look at this, is nitrate going to be happy being a spectator and let H plus do the oxidizing? No, this is wrong. Nitrate is a much more powerful oxidizer than H plus. And therefore, we call it an oxidizing acid because the anion turns out to be more powerful than the cation that oxidizes. Yeah. And so, but the situation is the nitrate requires how many H pluses? The nitrate requires 4 H pluses. Well, we got H plus present, and so this is just the ratio that they react in. And so since we have H plus present, then we're good. Because when I look at the inventory, there's H plus and nitrate. So nitric acid is what we call an oxidizing acid. Another oxidizing acid is iodate and H plus. When you have iodate and H plus, we form the acid HiO3. What is the name of this acid? Iodic acid. Iodic acid. Iodic acid is an oxidizing acid. Perchloric acid is an oxidizing acid. Chloric acid is an oxidizing. Chlorous acid is oxidizing. Hypochlorous acid is oxidizing. All those have anions that are electron poor. Sulfuric acid is an oxidizing acid. And so if we have an oxidizing acid, the single replacement method doesn't work. If I use single replacement gives me no reaction here for single replacement. But there is actually a reaction. And so let's use the chart method to figure it out. All right, so in the chart method, what is the first step? Inventory. So let me erase this here. It turns out that the assigned roles are wrong. And so what we're going to do is we're going to inventory copper solid, H plus, nitrate, and water. Then we look at the chart. Copper is on the right side there. It's a reducing agent. H plus is an oxidizing agent alone. And then we have H plus combined with nitrate. That's an oxidizing agent together. And then we have water, which is on both sides. So it's an oxidizing agent and a reducing agent. And then we pick the strongest oxidizing agent. So we look at H plus alone versus nitrate and H plus versus water. And the strongest oxidizing agent, based on the chart there, is going to be nitrate with H plus together. So that's what this bar indicates. This bar indicates that both H plus and nitrate are required for this to react. And then we look at copper. There's copper versus water. Water is way up there. It's weak. And so the strongest RA is going to be copper here. And water is just going to be a spectator in this particular reaction. And so the two half reactions here I'm going to write out. The first one is copper 2 plus 2 electrons yields copper. I have to reverse this. This is from the chart, so I must reverse it because my reactant is not copper ion. My reactant is copper metal. This is the reactant, not the product. And so the first step is to reverse this equation, so I have copper as the reactant, not as the product. Okay, so now I have copper as the reactant, which is what we should have. Okay, the second reaction here is going to be with nitrate, so I just copy it down. Over here, nitrate is a reactant. And so I have nitrate plus 4H plus. nitrate plus 4H plus how many electrons? Plus, reading off the chart, plus 3 electrons yields NO gas plus 2H2O liquid. Okay, now there's a mismatch in the electrons. Do you see 2 electrons here, 3 electrons here? So the electrons mismatch. If the electrons mismatch, I have to get them to match by multiplying. And so I'm going to take the first equation and multiply it by times, well, we're going to say times 3. And then I'm going to take the second equation here and then multiply that times 2. So if I multiply the first one by 3, I'll get 6 electrons. Multiply the second one by 2, I'll get 6 electrons to get them to match. And then add them together. So I'm just going to combine the 2 steps. So I'm going to get 3 copper solids. Okay, that's the reactant there. And then I'm going to combine it with these reactants here. Plus 2 nitrates, plus 8H plus 6 electrons. And so those are my combined reactants multiplied by these factors. And then what I'm going to do is I'm going to combine the products. Well, I'm multiplying by that factor here. So I'm going to do 3 Cu2 plus 6 electrons. Okay, that takes care of the products from the first half reaction. From the second half reaction, I'm going to get 2 NOs, so gas, plus 4 H2O liquids. Okay, then I need to find if there's a driving force. So the driving force is I'm going to rely on the conjugate relationship. If copper 2 is my oxidizing agent, then this has got to be the conjugate reducing agent. If nitrate and H plus is my oxidizing agent, then this must be the conjugate reducing agent here. That is, you know, in one direction it's an oxidizer, in the opposite direction these products are a reducer. And so both of these reactions can go both ways. And so we're trying to predict which way is favored, going left to right or right to left. And so we assigned them based on the chart over here. Copper metal, oops, this is wrong, sorry. This is, I'm supposed to be doing this one here, not this one. Copper metal is the reducing agent. This is my oxidizing agent here, going backwards. And so copper metal is my reducing agent. Nitrate and H plus is my oxidizing agent. The 6 electrons cancel. The copper 2 plus, this is my oxidizing agent in the reverse direction. And the NO in the water, this is my reducing agent in the reverse direction. And so let's compare the 2 oxidizing agents. Nitrate and H plus versus copper 2 ion. Okay, which one's stronger? So here's copper 2, and the nitrate and H plus are up here. Which one's stronger of an oxidizer? Nitrate and H plus. It's closer to fluorine. So nitrate and H plus is a stronger oxidizer than copper 2. That means the reducers must be the same because of the conjugate relationship. Copper metal must be a stronger reducer than NO and water. Water got cut off there, but it's closer to lithium. Lithium's down here, so copper metal is stronger. Reducing agent, this is a weaker reducing agent here. And so we have driving force. We're going from stronger to weaker. We expect this reaction to occur. If we did this by a single replacement, we wouldn't have gotten any reaction. And so the chart method is, we don't have to memorize exceptions. Like single replacement, we have to be aware, that single replacement, we have to be aware that single replacement fails for these types of acids. What are these acids called again? Single replacement fails for oxidizing acids. we have to be aware that single replacement is going to fail for something like chlorine. The elements on the right side of the periodic table they're going to fail for. It's okay if we have elements from the left side of the periodic table. But we don't have to pay attention to those things if we just use the chart method. And so the chart method is, we don't have to memorize all those exceptions if we just use the chart method. The disadvantage to using the chart method is it's a little bit more work, but not much. And so we're going to simplify this. Let's get rid of the spectators, which we did there. So the net reaction here is just the 3 coppers plus, actually this is okay. Yeah. So we kind of simplified it there. Let's do one more, and that's it. Well, this last one is another failure of the single replacement. Single replacement, when we go through this, we're going to predict we're going to form KCl plus Na. But actually, this one seems to work, but this is the wrong reaction. There's a driving force here because potassium is more active or less active than sodium. And so here we are, we're going to need a potassium solid and sodium solid. Potassium is more active. Sodium is less active. And so there's a driving force here. But this is wrong. It's wrong. And then I could do something like this. I could do sodium solid plus do potassium chloride. I'll do sodium solid plus potassium chloride. This should yield NR. This is wrong. The single replacement fails for both of these here. It's because the roles are misassigned. And so let's take a look at this one. Even though single replacement predicts a product and a reaction, the products are actually wrong. And so let's examine this one. Actually, both of these have reaction, but both of these don't have the reaction that's expected. And so let's take this one and do the chart method for this. If we use the chart method, we're going to get the inventory: potassium solid, sodium ions, chloride ions, and one more. What else is present? Water. So we use a chart. Potassium ions are reducing agent there next to lithium. Sodium ions, oxidizing agent. Chloride ions. Chloride ions are way at the top. Chloride ions are a reducing agent, and water is both, oxidizing agent and reducing agent. So what we're going to do is we're going to pick the strongest oxidizing agent. What's the strongest oxidizing agent? Sodium ions or water? And so the oxidizing agents are on the, what side of the chart? What side of the chart? They're on the left side of the chart. What's the strongest oxidizer? Fluorine. So let's start at fluorine and then see which one we hit first. Do we hit water first, or do we hit sodium ions first? It looks like I hit sodium ions. I don't even see water on there. Where is water on there? I've been telling you it's both an oxidizer and a reducer. You'll find water down here. You might think water is the weakest because it's at the very bottom of the chart, but it isn't. This is a separate second chart. And the separate second chart is because this is under basic rather than acidic condition. And in the second chart, how do we rank these? Well, we rank these by this number on the right here. You see the number for water is minus 0.828. Minus 0.828. That's its ranking. Minus, this got cut off here, but minus 0.828 puts it between these two. This is minus 0.763, this is minus 1.676. So it's in between these two here. That is, it's between zinc 2 and aluminum 3. Zinc 2 and aluminum 3. So this is what I did here on the chart. Do you see these three dots here? These three dots means water goes here. So what that means is water is a better oxidizer than aluminum ions, but a weaker oxidizer than zinc 2+. So water's here, sodium's here. Which one is a stronger oxidizer, water or sodium? Water. And so this got it wrong because it's telling, in single replacement it assigns sodium ions as the oxidizer. It's not. Sodium ions are not the oxidizer, water is the oxidizer. As far as reducing agents goes, potassium is the second, lithium is the first strongest reducing agent. Chloride is extremely weak. And so we expect the reaction to be between potassium ions and water. So we just copy the equation for water here. When water takes electrons, we'll have 2 water liquids plus 2 electrons. This is going to yield hydrogen gas plus 2 hydroxides. And then we'll take the reaction for potassium. But potassium we're going to have to reverse because potassium's like this. Potassium ion plus an electron goes to potassium solid. And so what we're going to do is we're going to reverse this, because potassium is the reactant. And so we need potassium to be the reactant. Potassium goes to potassium plus an electron. And then we see that the electrons mismatch. There are 2 electrons here, there's 1 electron here. And so what we're going to do is we're going to multiply the second one by 2 times 2 and then add it to the first one here. And so I'll just do this. I'm going to get 2 potassium solids. And then I'll add these reactants here, plus 2 waters, liquids, plus 2 electrons. Then add the products here. And so 2 potassium ions plus 2 electrons. And then add these, plus a hydrogen gas plus 2 hydroxides. And then I look for driving force. The driving force is most easily done from the half reaction. So water is our oxidizing agent, and therefore these are going to be my conjugate reducing agent. Potassium is my reducing agent, and therefore potassium ion will be my oxidizing agent, the conjugate for the reverse. And so now I can assign these. Potassium ion, reducing agent, water, oxidizing agent. Potassium ions, oxidizing agent, hydrogen and hydroxide, reducing agent. And then I compare. The 2 electrons must cancel, like they do here. I compare the oxidizing agents. Which one is a stronger oxidizing agent, potassium ions or water? Potassium ions or water? Water. Water is up higher. And so we're going from a stronger oxidizing agent to a weaker oxidizing agent. Water is a stronger oxidizing agent, potassium ions are weaker. And the reducing agents, potassium versus hydrogen and hydroxide, which one is stronger? Hydrogen and hydroxide are going to be up here. In here. This is what these dots are. And so potassium is stronger. And so this is a stronger to weaker, and therefore I have driving force. And so what I mean by simplifying is just getting rid of the spectators. So potassium solid plus 2 waters, liquid yields 2 potassium ions plus hydrogen gas plus 2 hydroxides. And we have reaction, this driving force for this. And so this is the reaction. The products are very different than single replacement. Single replacement predicted we form KCl and sodium solid. That's wrong. Single replacement predicts this is no reaction here. There is a reaction here. Can you figure out what the products of this reaction are? Here. Well, we could figure out the products of this reaction. The products of this reaction are, well, inventory: sodium, solid, potassium ions, chloride ions, and water. Sodium, the reducing agent. Potassium ions are an oxidizing agent. Chloride is a reducing agent. And water is both an oxidizing agent and a reducing agent. And we pick the strongest oxidizing agent, potassium ions versus water. The potassium ions here. Then water is up here. Potassium ions and water is up here with 3 dots. So water is a stronger oxidizing agent. And so the oxidizing agent should be water. So single replacement had this misassigned because single replacement would have put potassium ions as the oxidizer. And the reducing agent, sodium is here. Chloride is way up there. Top. So sodium is much stronger reducing agent. So this is what we're going to have. We're going to have sodium, solid, and water react. All right, the problem here is we have sodium on the product side, not on the reactant side. So what we need to do is we need to take this half reaction and flip it. So we're going to flip it so that sodium becomes a reactant. So sodium solid goes to sodium ion plus an electron. And then for water, we'll just take it as it was written before. 2 water liquids plus 2 electrons yields hydrogen gas plus 2 hydroxide. And then we're going to combine them. So the first one we're going to multiply by 2. So I'll just add them like this. 2 sodiums plus 2 waters. And the electrons are going to cancel. You're going to get that 2 times 1 is 2 electrons. Right? Yields 2 sodium ions plus hydrogen gas plus 2 hydroxide. And then we assign it like this again from the half reaction. So this is my reducing agent. This will be the conjugate oxidizing agent. If this is my oxidizing agent, this will be the conjugate reducing agent here. And so the reducing agent, sodium, oxidizing agent, water. Now if we reverse this reaction, going backwards, sodium ion is my oxidizing agent, and hydrogen and hydroxide will be my reducing agent. We compare the 2 oxidizing agents, sodium ion versus water. Okay, over here, sodium ions versus water. Water is stronger. So I had this over here. And so water is stronger, sodium ions weaker, and then sodium metal is stronger than hydrogen and hydroxide. That's weaker. So we have driving force here. So we expect. And so single replacement predicted no reaction. However, chart method, we do see a reaction. Uh-huh.
Why would you multiply it by 2?
I multiplied it by 2 because there's only 1 electron here, there are 2 electrons here. I have to get the number of electrons to match before adding it. I'm sorry?
It's from the chart.
Yeah, this is from the chart. The chart shows that sodium is 1 electron. And then if I go down, let me scroll down, water. I scroll down to water. Water has 2 electrons, so it's mismatched. We have to get it to match to cancel out. The electrons always must cancel because you can't go and buy a bottle of electrons. You know, it's not stable. All right, so those are the exceptions. The exceptions are because the roles are misassigned. And I give you the 3 common misassignments. One where A is non-reducer, A is an oxidizer. 2 where B is not the oxidizer, X is the oxidizer. And 3 is where water is the oxidizer. It usually happens when we have a very powerful lock. That's if you want to look. The safe bet is just to use the chart method. We could use the chart method for much more complicated reactions as well. And so let me just do one quickly, and then we'll review some more of these tests. We could do this one, like we could take FeSO4 plus HCl plus NaNO3. This looks like a metathesis reaction. Looks like metathesis. There are different ways we could handle this. We could do multiple combinations, you know, AB plus CD, and then AB plus EF, and then EF plus BC, you know, CD, whatever. We can try multiple combinations. This is not really a double replacement. We could do multiple double replacements, or we could just look for different metathesis. Like, for example, iron. What are the cations? We have iron 2, we have H+, we have sodium ions. What are the anions? We have sulfate, we have chloride, and we have nitrate. Yeah. And then we look for combinations for this. Like, for example, iron 2 chloride, does it precipitate? What's the solubility rules for chloride? Soluble except for silver, lead, and mercury. So iron 2 chloride does not precipitate. Iron 2 nitrate, what's the solubility rules for nitrate? They're all soluble. Nitrates are all soluble. What the rule is, nitrates, chlorates, and acetates are all soluble. What were the what are the solubility rules from the beginning? Tell me the solubility rules. Group ammonium and group 1, all soluble, good. Nitrates, chlorates, and acetates are all soluble. Yeah, chlorides, bromides, iodides are all soluble except for silver, lead, and mercury. Sulfates
soluble except for silver, lead, mercury,
Calcium,
calcium, barium.
Good.
Sulfide,
Hydroxides come then.
hydroxides are insoluble,
Yes.
except for carbon, ammonium,
And calcium,
strontium,
Good. And then after hydroxides comes sulfides.
except for group 1 and
except for group 1, group 2.
Yeah, except for group 1 and group 2. And then after sulfides comes the,
Phosphate, chromate, carbonate.
phosphates, carbonates, chromates are all
insoluble.
except for,
Group 1 and ammonium.
okay, good. So we go through this and there's pretty much no reaction from metathesis. There's no precipitate, you know. We try all the combinations. Although you might think of one combination that might work, and that is FeSO4. FeSO4 plus HCl. You might think this is a combination because FeSO4 plus HCl goes to what? Metathesis, double replacement. It'd go to FeCl2 plus H2SO4. Right, this is AB plus CD, so it'd be iron 2 chloride plus hydrogen sulfate. Hydrogen sulfate would be, what's this called? H2SO4. Hydrosulfuric acid is this. H2S is called hydrosulfuric acid. H2SO4 is called sulfuric acid. And then we compare. We go to the acid chart and we compare. The acids, HCl versus H2SO4. Which one is a stronger acid? HCl. But then we would recall the effect. What was the effect called? What was the effect called? Starts with an L. The leveling effect. Tell me about the leveling effect. Would you guys be prepared to answer a question like that? What is the leveling effect on this test? Or were you keeping your fingers crossed that it wasn't going to be on this test? Tell me. If I made a 20-point question, what is the leveling effect? Would you be able to answer it, or would you be blown out? Should I put?
No.
I shouldn't put it because you didn't bother studying it, the leveling effect? That's from the chapter 8 and 9 discussion. Yeah, that's what you can kind of expect. You know, at UCLA, you get a 20-point question. What is the leveling effect? It wasn't in the book. It was in the lecture. You know, and then you get blown out. You're lucky, though, because I didn't put the leveling effect, because I know I would have blown out like a lot of you guys, because you aren't reading through the notes. And so, but you know, it happens. It happens that I got blown out myself when I transferred to UCLA. I was crushed. You know, I was crushed because I didn't study. I didn't study the right way. So that's why I say, you know, it's so important to do that. I mean, can anybody answer that? What is the leveling effect? No, all the acids are going to be soluble. All of these acids are going to be soluble. All of them. I was talking about when I was talking about electrolyte properties and that kind of stuff, but it's all right. Basically, what it says is that all strong acids have the same strength in water. All strong acids have the same strength in water. I'm not going to ask you about the leveling effect for this test. I'll tell you. So it's always a gamble, what you study, what you don't study. But what the most important stuff I found to study is the stuff that's presented in lecture. And so I wanted to know everything in lecture before going to the test, because if you review, let's say, I talked about the leveling effect like 2 weeks ago. If you reviewed that every day, you read that, in your notes, leveling effect, all strong acids have the same strength in water. Day 1, day 2, all strong acids have the same strength in water. It's just like repetition. So by the time the test comes, you'd have it ingrained in your memory. But I don't know what it takes to get the point across, but I'll probably shut up from now on. But you want to be aware of that things. And so this is an example of the leveling effect. For weak acids, we don't have to worry about the leveling effect. We just look at the chart. For strong acids, there's a leveling effect, and so these are the same. They're tied, kind of thing. Although H2SO4 is a little bit different, but we're going to take it as a tie. And so that means there's no driving force for this one either. No stronger to weaker acid. That goes the same here. I mean, when we add H plus and NO3, so if we take the next one, HCl plus sodium nitrate, HCl plus sodium nitrate, this would give us sodium chloride plus HNO3. What is HNO3 called? Nitric acid. So what's stronger acid? HCl, what's HCl called? Hydrochloric acid. Which one's a stronger acid? Hydrochloric acid or nitric acid? And you would say? But you would be wrong because of the leveling effect. The leveling effect says all these acids are going to have the same strength in water. Okay, but it's still, since it's still new, it takes some more time. I'll give you more time to absorb this. So you aren't going to be tested on the leveling effect on this exam. But the next one, I can't, because the next one we're going to have chemical reactions as well. And so the next exam, you might. So just be aware what that is. So actually, we go through this, and there's no reaction for metathesis. If there's no reaction for metathesis, then what do? I try all the combinations. And then see there's no driving force. That's metathesis. You try all the combinations. Double replacement is just because we have a certain number, but sometimes we've got to do triple replacement, quadruple replacement. We just got to keep looking until we see an ion combination. So we try all the combinations. Try all the combinations. So I try all the combinations, see if there's no reaction. So if there's no reaction for metathesis, then what do? I go to what are the other two types of reactions I have? Redox and so which one should I go to first, redox or acid-base? I go to acid-base. In fact, that's all you're going to do on this test is Bronsted acid-base. So Bronsted acid-base, what are the steps in Bronsted acid-base? So if I get no reaction for metathesis, then I'm going to start looking for a Bronsted acid-base reaction. And that Bronsted acid-base, what are the steps? Somebody asked me, do we, 7 steps? It's a lot of steps, but what I'll do is I'm going to try to combine those steps so it's not as many steps. And so the first step is to inventory. So what do I have? I have iron, 2. I have sulfate. I have H+. I have chloride. I have sodium ions, nitrate ions, and what else? And water. Do iron 2 ions appear on the chart? No. And so we're going to put an N. Do sulfate ions appear on the chart? Yeah. Sulfate ions appear here. Is this the base side or the acid side? This is the base side. So sulfate is a base. Yeah. H plus appears on the chart. Do you know where H plus is? H plus is here. Is H plus in hydronium? Same thing. In fact, is H plus stable? If I asked you to explain why H plus is not stable in water, could you? Just a brief explanation. Why is H plus not stable in water? Did you review that part of the notes? Uh-huh. Yeah, what is so concentrated? What in the proton is so concentrated? There's something, yeah, you're right, it's concentrated. The proton's very concentrated, both in mass and in charge. Yeah, the charge is the concentration of the charge is way too high. It's very reactive. That's good. That would have been pretty good. Anybody add to that? Yeah, like I said, it's always a gamble what you study, what you don't study. But you know, what I found at UCLA is they don't give tests with lots of questions. At UCLA, they give tests with like 4 questions. Each question is worth 25 points. One question might be, why is the H plus not stable in water? And if you can't answer that, you're already down to a C. You know, which is harsh. This is why my tests are so long. You know, if you can't answer that, then it's not going to kill you. But if you can't answer that, that's okay, because I didn't put it on the test, this test. Because I know we're just starting out, and you're probably emphasizing the book. You don't want to emphasize the book, because what you're going to find is when you transfer, they don't emphasize the book. They're going to emphasize their lecture for the exams. Okay? And so H plus is the same as hydronium. That's an acid. Chloride is a base, but chloride's too weak really to be a base. It's on the upper right. You've got to know that. Sodium ions, these are N. Chloride is a base, borderline N. Nitrate is a base, but it's also in that region. That region, you know, with the strong acids. The conjugate bases of the strong acids are too weak to be called basic. And so nitrate's very weak. Water is a better base. Water is a better base than chloride. Water is a better base than nitrate. And so that's telling you something. And so water is both an acid and a base. So what's the strongest acid? What's the strongest base? H plus is the strongest acid. And the strongest base would be? Well, here's H2O, but I see that, you know, sulfate is better. Sulfate's a better base. And so it looks like this is it. And so the reaction is going to be H plus sulfate goes to, well, in this case, it's just going to go to HSO4 minus. HSO4 minus is interesting. It's both an acid and a base. And so one way of doing this is by hydronium. And so here we might need hydronium to better understand this. Because if we have hydronium plus sulfate, the hydronium is going to lose a hydrogen to form water, and the sulfate will gain a hydrogen to form what? HSO4 minus. So the acid loses a hydrogen, the base gains a hydrogen. So this is my acid, this is my base. Now, unlike redox, when we reverse it, we don't look at the half reactions, although you could have the half reactions. What we do is we look at these. So water going backwards, does it lose or does it gain going backwards? So water ends up going to hydronium. So it gains. So that means it's the base. Bases gain proton. Acids lose the proton. So HSO4 minus, when we go backwards, loses the H. And so that's our acid. Then we compare the two acids. Which one's a better acid, hydronium or bisulfate? What's another name for bisulfate? Hydrogen space sulfate. And so what's a better acid, hydronium or bisulfate? Hydronium. So what we're doing is we're going from stronger acid to weaker acid. That means the bases must do the same. So sulfate versus water. Sulfate is a better base than water. The strongest bases are down at the bottom. And so sulfate is a stronger base than water. It's a weaker base. And so what we have is we have driving force here. And so there was no metathesis reaction, but there was indeed a Bronsted acid-base reaction. And so Bronsted acid-base reaction occurs here. The reaction is going to be between hydronium or hydrogen ions and sulfate. Now, there's also a redox reaction that occurs here. That can be solved using the chart method. So if you have time over spring break, try this. Try to figure out what the redox reaction is using the chart method. The chart method is very similar to the Bronsted method for acid base. Okay, are there any questions for this? What I recommend is, it seems like you're still pretty fuzzy on the solubility rules, so before the test, why don't you review those? And then I'll pass out the test pretty soon. So you can take a break and then just do some last minute studying.